Tonight, the quantum universe. Like to always start with the big picture that this 5-month series, we are examining the relationship between science and faith, so no surprise there. And you may remember that we've spent a big hunk of time, the first 10 weeks, looking at this relationship between science and faith, kind of defining the terms, and then kind of tracing how those two have kind of interacted with each other across the centuries. And then 4 weeks ago, counting tonight, we shifted. We're spending about 6 weeks looking at some particular areas of science from a contemporary viewpoint, kind of where we are and kind of what those are contributing to the conversation. We started this section with a session on geology and paleontology and the concept of deep time. We then shifted over, talked about Einstein's 5 papers he wrote in 1905, the miracle year, and then kind of focused the latter part of that on really the theories of relativity, both specific and general. And then the last 2 weeks, we've looked at the issue of cosmology, also which come out of Einstein's work, the idea of the Big Bang, and then we spent another week on the anthropic principle last week. So today we're going to shift our attention from the very large, the cosmos as a whole, down to the very small, the subatomic. And I want to just put something on the table here. When we make this shift, what we're really dealing with quantum physics is the fundamental nature of reality. What is real? What is real? What is the essence of the universe itself? And that is the realm of quantum physics. It's hard to, we need to remember, it's kind of a hard thing to realize. It was only in the year 1905, and with Einstein's paper on Brownian motion, that we really had evidence that atoms, in fact, did exist. You may know that there was a group of Greeks in the 4th century BC called the atomists who actually sort of postulated the idea, and that idea had been kicked around a lot, over time. But it was only in the early 20th century that we really knew that there was such a thing as atoms. Later, we learned that atoms were not what we thought they were, which was the smallest and most fundamental thing that existed. That in fact, there are things that are smaller than the atom. And so we knew about protons, neutrons, which make up the nucleus, and then electrons, which travel around the nucleus. Then we learned that not even these were the most fundamental elements of nature. So here you have a GIF of a proton, which would contain 2 up quarks, a down quark, and you're going to have gluons kind of holding them together. So even within that, the part of an atom called a proton, I'm sorry about that. Yeah, proton, it's actually made up of other things. And that was sort of an eye-opener. Today, this chart is what you can see out there. This is what is known as the standard model of elementary physics, which has only recently been completed. You may have heard about the Higgs boson. It was called the God particle, that not too many years ago, they actually at CERN had evidence that in fact that particle does exist, which gives mass to the universe. And if you look in there, the first 3 columns, these are the elementary particles that make up matter as we know it. We have quarks and we have leptons. And then the 3 columns in the red box are actually the exact same thing, but reverse charges. This is what we refer to as antimatter. So there's an antimatter particle for each particle of regular matter. And then on the far right, you've got what are called the force carriers, which are the bosons. So today, the standard model has 30 elementary particles that then make up everything else. Quarks and leptons, also known as fermions, being the basic building blocks of matter and antimatter. Boson as the force carriers. And so that's the standard model. But for our discussion for today, what's important is not the particles themselves, but the physics of how they behave. And that's where things kind of really get interesting. Now, when it comes to the subatomic world, some of you used to play with these kind of things, have them on your desk. You know, you swing one ball, it kicks one ball out the other end. You swing two balls, it kicks two balls out the other end. And this is basic Newtonian physics. But when it comes to the subatomic world, to the quantum world, our ordinary or our Newtonian physics simply breaks down. And we find that the fundamental laws of the universe, as we know them in our world, no longer apply. And that was a real shocker. We find ourselves in the strange world of what is known as quantum physics. Of course, quantum mechanics deals with that. Now, here are some things just to think about as we begin. Quantum physics, this is just some facts. The non-Newtonian physics of the subatomic world is, without doubt, the most successful theory ever developed by science. No argument there. In fact, quantum mechanics is the most successful set of ideas ever devised by humans. Not a single prediction of quantum theory has ever been proven wrong. And so far, every test that's been done has proven it to be correct. You'll find this information in any book about quantum theory. I mean, that's an amazing record. Quantum physics provides the very framework upon which our contemporary view of reality is based, as well as all of the technology we enjoy today. You may not think about that, but here's the simple version. If it's electronic, it is built on the principles of quantum physics. And we live in an electronic world, so we live in a quantum world. Our best science tells us that we are part of a quantum universe, that this is the nature of reality, down there at that, almost the Planck level down there, the very, very lowest level. That's the nature of the universe. And that quantum theory is the best tool we have for understanding the fundamental nature of reality. All of these statements you find pretty much in any book on quantum theory, quantum mechanics. Now, the practical applications of quantum physics are not controversial, such as electronics. We simply enjoy all these things every day and probably don't give it a second thought. But the implications behind the theory are just breathtaking and staggering, so much so that for many scientists, they literally border on being unbelievable. Perhaps the best way to kind of launch into this radical nature of quantum physics is through some of its creators. We'll start with the guy who actually wrote the paper, got all this started. Albert Einstein won the Nobel Prize for the paper that laid the foundations for quantum theory. He was repelled by some of the implications that the theory he helped create put forward. One that got him in particular is something he called spooky action at a distance. We're going to talk about that a little bit more, but just for now, just be aware, Einstein's paper, the math sort of presented this, and he said, didn't like it. Niels Bohr, one of the pioneers of quantum physics, this is a quote from him. Anyone who is not shocked by quantum mechanics has not yet understood it. Richard Feynman, another well-known figure, a little bit next generation, but well-known figure in quantum mechanics. I think it's safe to say no one really understands quantum mechanics. So Al, when we get done, we'll see what you think. Do not keep saying to yourself, how can it be like that? And I think in a few minutes, when we talk about some of the things, some of the characteristics of this, you have those moments like, what? How can that be? If you do that, and then he mixes his metaphors here, but you'll go down the drain into a blind alley from which nobody has yet escaped. So there's something about quantum physics that seems counterintuitive. Now, there are 5 key elements of quantum physics that stand in sharp contrast to Newtonian physics, and they have found their way into discussions about science and faith. So what we're going to do tonight is basically kind of walk through these 5 and then kind of look at some comments from some people from the religious community as they kind of dialogue with this science. Here are the 5. quantum duality, indeterminism, non-locality, quantum entanglement, and the quantum enigma called the observer effect. Now, as a non-physicist, my job tonight is to see if I can actually walk us through these in a way that we can all understand in a non-technical sense. So here's the first, quantum duality. Little backstory. Quantum theory was first proposed by Max Planck in 1900. The core idea was that it's simple enough that energy exists in packets, or quanta, because previously it had been thought that light and energy existed in waves. That was the prevailing scientific view. So the question was, which is right? Is it waves or is it packets, quanta? Now, Max Planck, interesting enough, proposed the idea as a fudge, as a way to make the math work. He did not think that quanta actually existed. So this is a little mathematician's trick. He wanted to kind of make the math work. So like Einstein would do later, and one of his famous problems, he would slip something in that made the math work, but not necessarily thinking it was real. 1905, the miracle year, one of the papers the 26-year-old Einstein published was on the photoelectric effect. The paper took Max Planck's idea that light existed in packets or quanta and then developed it into a full-fledged theory. So in the paper, Einstein demonstrated that light actually existed as quanta. It's not something you just sort of slip in there to make things work, that is in fact what it is. This paper, of course, laid the foundations of quantum physics. Now, the math said that light existed in packets. What was needed is some good laboratory empirical evidence to back it up. This led to the famous double slit experiment. This is also known as the most beautiful experiment ever devised. You can buy books just about this. This experiment is still being done in a variety of different kind of ways. We'll see several of them tonight. Now, here's the scenario. If quanta, photons or electrons, both energy, were fired through two slits and they were particles, you can imagine a shotgun or a machine gun, something just shooting away, and the bullets are going to be stopped except where the slits are, the result should be two stripes. That's pretty straightforward. If they're particles and you fire them through a double slit, you should get two stripes. If they were waves, you're going to get something different. Because when a wave goes through two slits, you have a wave coming out each of the two slits, and so you now have two waves, and those waves then are going to interfere with each other. At times they're going to be negating each other. At times they're going to be reinforcing each other, so areas of strength, areas of weakness, and you will get what you see on the right, that type of a pattern. So clearly, two very distinctive different patterns, depending on if it's a particle or it's a wave. So run the experiment. Are you going to get 2 bars or are you going to get a barcode? Here was the result. So what do you think? But this was inconclusive because particles might, not sure, but could be colliding with each other. And it's possible under certain circumstances that particles might actually produce the image that we see. So the test was amended so that you can only fire 1 electron at a time. This eliminates collisions, or the technical term is interference. So now we're going to get a cleaner result firing them through. The result, same thing. This demonstrated that light and quantum objects like electrons or like photons were actually waves. They're behaving like waves. So far, so good. Still a problem. The problem was that Einstein's paper on the photoelectric effect said that the math indicated at the quantum level, objects existed both as wave and as particles. This is what's known as quantum duality. Duality being wave and particle. Now, particles and waves in the Newtonian world were thought to be mutually exclusive categories. A particle is a particle, a wave is a wave. They are not the same thing. They are, in fact, two different things. So the thought that something could be both was a bit troubling. How can something exist in two mutually exclusive categories? It can't, not in the Newtonian world. But Einstein's equations said that it did. And science had learned to trust and to follow the math as much as the experimental physics in the laboratory. This was still weird, but even weirder, the math also said that because a quantum object is both wave and particle, it should be able to go through either slit and hang on, or both at the same time. But how can something exist in two places at once? In the Newtonian world, the world we live in, it can't. The math said it could. Back to the double slit experiment. The experiment was amended so that what was actually happening at the slit could be observed. This is the difference. The result defied belief. The experiment was exactly the same. The only difference was that now we have an observer looking at the results real time as it's happening, watching what was happening at the slits themselves. When the object was observed, something extraordinary happened. The result changed. Same experiment. Nothing has changed except adding an observer, and the quantum object changed what it did. Makes no sense in the Newtonian world. It changed from this to that. Imagine the guy who was there that day. The objects that had previously produced a barcode now produced two stripes. This meant that objects that had previously acted as waves are now acting as particles. By the way, same objects. We didn't change objects here. This demonstrated two things. First, it demonstrated quantum duality, that at the quantum level at least, objects can be both particles and waves. And that at the quantum level, objects have the ability to be either. And they somehow, and then we begin to get this weird language. You get language of they somehow choose which to be, which is not language you normally use with objects. And the trigger for the change simply seems to be the act of observing. This is called the observer effect. We're going to pursue that separately here a little later. The other result we need to hold off on for a while, for a few minutes. For now, we need to move on to the next implication of the experiment. This is quantum indeterminism. So first one is duality. Something can exist both as a particle and as a wave, and somehow another can flip back and forth. In the subatomic world, the quantum realm, objects appear not only to exist in two mutually exclusive states, wave and particle, they also appear to be able to change states, flipping between wave and particle, without any sufficient mechanical cause. Now, let's repeat this statement. Without any sufficient mechanical cause. This is a quote. Now, this was a game changer. This means that at the quantum level, one of the most fundamental laws of the universe, the law of cause and effect, no longer seems to hold. Whereas determinism, cause and effect, was one of the foundations of Newtonian physics and the world we live in, indeterminism is one of the foundations of quantum physics. Instead of cause and effect, physicists began to speak about particles as being strange language, conscious, making choices, and bringing things into existence by their choices. This is particles and waves we're talking about. Number 3, quantum non-locality. To understand non-locality, we need to remind ourselves of what is meant by locality, which is an idea that we have in Newtonian physics. Locality is another fundamental principle of Newtonian physics and the world that you and I live in. Under locality, all objects have a single location in space at a particular point in time. The old joke, you can't be 2 places at the same time. If objects are here, they cannot be there, at least not in the same moment. That's locality. Again, objects cannot be in 2 places at once. They are limited to 1 location. That's Newtonian physics. Further, an object can only be affected by its immediate surroundings. So the further away an object is, the less influence it has. And if it gets closer proximity, it can have more interaction. Further still, communication between 2 objects is limited by the speed of light. Speed of light being one of the absolutes of the universe. That's the world you and I live in. Okay, let's go back to the quantum world. Again, this is the Newtonian world. Quantum non-locality negates all of this. Just think about that for a second. In the subatomic world, the quantum realm, reality is fuzzy and ill-defined. You may remember Heisenberg's uncertainty principle. In quantum reality, you cannot tell where something is, or even what something is. Is it a particle or is it a wave? And it's even asserted you cannot even tell if something is. This also goes back to Heisenberg. Non-locality, again, predicted by the math. This could be tested, and it was. 1997, researchers at MIT put a clump of several million atoms into a quantum state and demonstrated that they were in 2 places at once. The experiment has been repeated over and over many, many times, larger and larger amounts of material over greater and greater distances. At the subatomic world, the quantum realm, objects can be 2 places at once. In some of the literature, I've seen numbers as high as they can be 30 places at once under the right conditions. They can even move 2 directions at once. They can also communicate instantaneously, regardless of the distance, not limited by the speed of light, which is essentially to say that all of the normal rules that you and I know that work in our world simply fall apart in the quantum world. And now we're dealing with a different physics. We're dealing with quantum physics. This means at the quantum level, the quantum realm, all of the laws of physics, Newtonian, simply cease to work. But this could only be true if these interactions were happening somehow outside, again, the language starts to break down here, but outside time and space as we know it, or outside the laws of the universe as we know it. And again, the language here gets you just not quite sure what to do with this. Now, just as the Big Bang Theory held that the origin of the universe lies outside or beyond, again, these are just approximate language of the universe, non-locality means that quantum physics deals with a reality that is also outside or beyond or somehow other than the universe as we know it. 4, quantum entanglement. Quantum entanglement is sometimes referred to as the God effect. According to this principle, not only can an object be in 2 places at once, but when 2 objects are entangled at the quantum level, that is, they're made to interact with each other, they remain entangled, even when they're separated. No matter where they are, no matter how far apart they are, And this means that when you do something to one of the entangled objects, the same thing happens to the other, no matter where it is, any place, theoretically, in the universe. And it happens instantaneously, seeming to defy the speed of light. This means that information, at least, can be teleported. Teleportation is no longer science fiction. Some of us grew up with Star Trek. We used to watch this and have the sound effects and all that, you know. It's been done, folks. It's been done for over 40 years. In May of 2012, for example, quantum teleportation was done between two of the Canary Islands in North Africa, La Palma and Tenerife, at a distance of 89 miles. In May of this year, quantum teleportation was done by the Chinese at a distance of 870 miles to a satellite in orbit and down to another location. These two towns, I will not attempt to pronounce them. Of course, this has some practical implications, as everything quantum physics does. For example, imagine a military communications. Imagine that you can send a signal and it cannot be intercepted, and therefore the code cannot be broken. I think any military person would be very interested in that. You know, there is no signal to intercept. There is no in between. Currently, quantum entanglement is the idea being used to develop both quantum computing and the quantum internet, both of which are being worked on. Another implication of quantum entanglement is that reality is not actually made up of particles. Now, this again runs counter. In the Newtonian world, we think of the universe as being made up of atoms and so it's particles. But in this understanding, reality is not so much particles as it is entangled relationships. And so some of the literature in quantum physics is about, that reality is basically information, not things. This leads to the weirdest aspect of quantum theory. It's called the quantum enigma. For this, we have to go back to the double slit experiment and to the observer effect. In the subatomic world, the quantum realm, things do not exist in the normal sense that we use that language. Here's Werner Heisenberg, who commented this a long time ago. The atoms, or elementary particles, themselves are not real. They form a world of potentialities or possibilities rather than one of things and facts. Again, that's a very different world from what you and I live in day to day. Instead of objects, the subatomic world is made up of what are referred to as probability wave functions. As probability wave functions, quantum objects exist, so the theory goes, in all their theoretically possible states at the same time. Again, this is not the kind of thing that we normally think of. It exists, and the language says, as a cloud of possibilities. It requires consciousness, or in the experiment, the observer effect, to, and the language becomes collapse the wave function, that cloud of possibilities, from this world of what it could be into a very specific reality. This was the second conclusion of the double slit experiment. The only thing that changed was there was an observer. So there is an observer effect. The very act of observing seems to produce a change. The enigma is that reality, at this point, is created at the quantum level by observation or by consciousness. And you can see why some religious folks might sort of find this interesting. Reality, in this thinking, does not exist until it's brought into existence from the cloud of possibilities by a mind. Only when it's observed does the cloud of possibilities collapse into one definite state. An example from Gestalt psychology, not literal, but this is just an example to give us an idea. For example, when we look at this piece of art, it exists in two states, to use the language. If you look at the black, you see a vase. If you look at the white, you're likely to see two faces. The point of this experiment, of course, is that it's only when we focus on one object that it, in a sense, comes into being. And the other possibility ceases. So I see faces, the vase vanishes. I see vase, the faces vanish. It is our consciousness, our mind, that brings either the black vase or the two white faces into being. Both exist potentially in this art. It's consciousness that literally creates one or the other. Now, this is an example from psychology, from perception. We all studied it in school. Quantum physics, at least some interpretations of quantum physics, says that this is the nature of reality itself. Consciousness literally creates reality. In the double slit experiment, the same thing is happening. Consciousness, the observer, causes objects to be a particle or a wave. And since everything is built from the quantum level, quantum reality applies to everything that exists, even the universe itself. So goes the argument. Now, here's another place where it gets interesting. Of course, there are many interpretations of what all this means. There is not any argument about what's happening. The arguments really come about, well, what does it mean? And for example, Einstein and a group of them would be called realists, and another group would be called anti-realist, and they come up with two entirely different conclusions about this. The view that it has been predominant for several decades, but now is losing some of its grip, is known as the Copenhagen Interpretation, because the scientists at Copenhagen, some of the great founders of quantum physics, took this approach. In the Copenhagen Interpretation, which is an anti-realist view philosophically, they're going to argue, well, we can't know anything about what's really going on. All we know is what our instruments tell us. We don't know what's behind it. We just see results. That's all we can know. We just see results. We don't know what they mean. We don't know that they have any connection with reality. We simply do not know that. And more importantly, our experiments do not tell us anything about the universe itself. So that's an anti-realist approach. Einstein, Schrodinger were realists. They didn't like this approach. Niels Bohr and some other, Heisenberg, Niels Bohr took this view. Others take a realist view. Einstein was one, Schrodinger was another, saying that our experiments are telling us about the nature of the universe itself. Now, let's just run with this for a minute. If this is true, if this interpretation is true, and what we're actually getting is data about the universe itself, about reality, then the universe, at least down there at the quantum level, is one heck of a strange place. Some postulate that if consciousness is the basis of reality, and if consciousness brings reality into existence, there must be, so goes the argument, a transcendent consciousness that is required to be the underlying cause of the universe. Any remotely religious person, your ears are going to perk up there. A transcendent consciousness that lies behind all that exists in each and every moment. This is further reinforced by other aspects of quantum physics. Both non-locality and quantum entanglement allow for the various parts of the universe to interact instantaneously. And this means the various parts of the universe can interact holistically. The closest analog, the closest analogy that we have to something that would do this would be a mind or a brain. Just think about that for a second. I didn't create that. This is out there in the literature. This is something that quantum physicists and others have picked up on. So, for example, Frank Welzig, MIT Nobel laureate in physics. The relevant literature on the meaning of quantum theory, again, not the quantum theory itself, but what it means, its interpretation, is famously contentious and obscure. Now, that's true. I believe it will remain so until someone constructs within the formalism of quantum mechanics, within the science, in the math of this, an observer that is a model entity whose states correspond to a recognizable caricature of conscious awareness. Now, this is carefully avoiding any religious language. That is a formidable project extending well beyond what is conventionally considered physics. So you might have to go outside physics to provide that answer. The physicist Freeman Dyson is one of those who takes this a step further to its logical conclusion. Again, he's a theoretical physicist, he's a mathematician. Here's what he says. The universe shows evidence of the operation of a mind on 3 levels. The first level is the level of elementary physical processes, as in quantum mechanics. That is, you look at that and look what's going on, but back up, In other words, you have evidence of operations of a mind down at the quantum level, at least an analog of it. Matter in quantum mechanics is constantly making choices between alternative possibilities according to probabilistic laws. The second level, which we can detect the operations of a mind, is the level of direct human experience, our minds. It is reasonable, he believes, to believe in the existence of a third level of mind, a mental component of the universe. If we believe in this mental component, and if we call it God, then we can say that we are all small pieces of God's mental apparatus. Now, of course, at this point, physics is blurring the line with philosophy, metaphysics, and theology. And again, it's not the physics we're talking about here. People are trying to say, what does this mean? Some within the scientific community itself find themselves using religious language. We just saw some examples of that. It should not be surprising that on the other side of the bench, many within the faith community, or at least some, see within quantum physics and quantum science as a whole, not something that we are in conflict with, but something that potentially could be helpful to us. And this may be one of those examples where the official position of the Methodist Church sees science and faith as complementary, not contradictory. That science brings something to the table and that faith brings something to the table. And as Dyson Freeman would say, that those two can come together. Again, this is not at the science level. This is at the interpretation level. So next week, we're going to deal with the boundaries of theoretical physics, what is called the unified field theory, string theory, loop quantum gravity. But for now, good Lord, we've got enough on the table.